for those who've joined. This is our October edition of the AESIN Tech Talks. This is a monthly series we started back in 2022, and we've grown steadily coverage. So without further ado, Matt, I'm going to hand over the stage to you. Thank you.
Oh, perfect. Thanks for the introduction, Gunny. I'll just share my screen. I'm going to talk to you today a little bit about accurate thermal simulation for the thermal management of an electric drivetrain. And I'm going to talk about it a little bit in the context of one of Cadence's software tools, which is called Celsius EC Solver, and that's just a CFD tool for doing thermal simulation of electronic systems. So let's jump straight in. So just to give you a little bit of an introduction to thermal simulation, to those of you who might not be too familiar. First, we'll begin with the design considerations for an electronic vehicle. So generally, when you're designing an electronic vehicle, you're aiming to deliver an equivalent, if not better, driving experience to traditional ICE vehicles without compromising on things such as range, performance, or like cabin creature comforts, that type of thing. So thermal simulation lets you solve for the three mechanisms of heat transfer, so conduction, convection, radiation. And if you're using the Cadence tool, Celsius EC Solver, you can solve models that are steady state. So just working out like if you leave something long enough, what temperature does it arrive at? We can consider transient models. So how long do things take to heat up and cool down? What are the temperature variations over time? In terms of material properties, we can consider both fixed properties and temperature dependent. So the types of material used in power electronics, for example, often has temperature dependent properties, and power dissipations will increase depending on their temperature. Basically, three keys to building an accurate model. So firstly, you need to choose the appropriate models. So that's in terms of like the numerics of how the simulation works. Choose the wrong set of numerics, and you might have something that's not appropriate to the use case and is going to give you bad results. You need to minimize the number of assumptions you're making. So the more things that you know up front, and the less simplification you have to do to your model, that's going to minimize the number of assumptions and make what you're simulating closer to reality.
Thank you very much for that. Yeah, very interesting talk. Some things I've worked with before in my historic past of being a more technical engineer. So yeah, I found it very fascinating actually, some of the developments that have happened. I don't know if there are any questions from the audience. I've got one or two that have come through, and one or so of my own as well. So on that, to ask you about when you're working with a customer, when a customer brings a design and then there's a model created, let's say in CATIA, and then you've got to now correlate it. What's the process, and how long does it take to get a good correlation of a prototype design with an experiment to then come back to the model itself and see whether the model's good or not?
So typically the process is when you start out with one of these simulation tools, you typically will you'll have a set of measurements from perhaps a prototype, so you'll know the conditions under which something was measured. You'll build your model and you'll simulate it under those same set of conditions, and try and understand, are there any differences?
Just
Where are the
around
differences?
configuration, you talked about, I had a question on acceleration and use of cores, which you answered perfectly with the graph that you showed earlier on. But when you're configuring your simulations to run on different platforms and different numbers of cores, how onerous is that process? I mean, is that something, again, that's quite straightforward, or you provide help with?
So if you want to hook up to something, to like your HPC, and you want to solve on those very high core counts, We have tight integrations with Microsoft HPC Pack and also IBM LSF. So we've got